Hey everybody, it's Nelson here again, here to talk to you about some more circuit things, this time nodal analysis by inspection. And you may ask yourself, what is nodal analysis by inspection? And that's a very good question, thank you for asking. Nodal analysis by inspection is just like nodal analysis, except for we skip like 2/3 of the steps. How awesome is that? And you're probably saying, yeah, that's pretty awesome. I like that a lot. Why did we even learn the other way? And the reason we learn the other way, besides the obvious answer, if you need to know where this comes from, is that nodal analysis by inspection, unfortunately, does not always work. It only works for nice, well-behaved circuits. But the thing is, a lot of circuits are nice, and a lot of circuits are well-behaved. And if you see them around, you can just be like, I got this, and then do it in 30 seconds like a rock star, and everybody around you is going to be like, oh yeah, you're awesome, everybody loves you, we want to give you high fives. And you're going to be like, yay, I did it, I'm the best, I'm so smart. Because you are going to be so smart when you learn how to do this. So let's get started, shall we? This right here is the exact same circuit and the exact same matrix equations that we had in the last video. I just redrew them because I feel like this is a good way to give you an example of what we're doing. You may have noticed in the matrix equations certain patterns, or like you can sort of visualize where all those numbers come from. And if you hadn't done that already, don't worry. I'm going to show you how to do it. It's really cool. So, what we have this vector, right here, which is the vector of unknowns. But we also have this vector right there, and this matrix right here. And you may notice something about these. This vector is a vector of sources. Everything in there comes from a source where we know what the value is coming out of it. And then you may have also noticed something about this matrix here. All those numbers in there all come from the different resistances in this matrix. And if you did notice that, you're very clever, and I'm very proud of you. Good job. So we can sort of think of these matrix equations as a table, or you don't have to, but it's a nice way to visualize it when you're getting started with this. So what I like to do is go V1 here, V2 here, and sources. And then V1 and V2 here. And of course, this one is V1 and this one is V2. So if you want to know what any specific box is, what you can do is, let's say, like, take for example this 3 here. Where is this 3 coming from? I don't know. Well, you can say that it's from the KCL equation we wrote out at node 2. What are the sources? What are the sources at node 2? Hooked into node 2 is a good way to think about it. And what are the sources? Well, there's this guy right here, 3 amps. Now, is that the same number as in this box? Oh, it is. And that's why. It's because it's 3 amps up there, so it's 3 amps down there. 3, 3, good stuff. Really easy to figure out. What about this negative 12 over 6? What's this guy doing here? That doesn't look as nice as the number 3. I don't know about this. Well, what sources are hooked into node 1? Well, there's this 12 volts right here. So why is it not just negative 12? And the reason it's not negative 12 is because these equations, remember, are coming from KCL, which is current. So they're all current equations. And that, my friend, is a voltage source. And volts are not the same thing as amps. Unfortunately, actually, probably very fortunately, they're not the same thing. So we need to do something to convert them into amps. And what's Ohm's law again? Say with me now. The voltage is the current times the resistance. So if you want to find the current, it's just the voltage divided by the resistance. Oh, hey, check it out. Negative 12 divided by 6. Whoa. It's as simple as that. How cool is that? And that's already one of the vectors already done. So then you may be like, okay, well, how do we deal with this big guy over here? This guy looks gross. I don't really want to deal with that. But it's actually not that bad. This is what we refer to as a conductance matrix because it's a matrix of conductances. And if you don't know what a conductance is, basically the conductance is the reciprocal of resistance. Resistance, of course, being measured in ohms, and conductance being measured in Siemens, SIEMENS, I'm pretty sure. And so if a branch of a circuit has 6 ohms of resistance, actually I'm going to do 5 because 5 is an easier number. If it has 5 ohms of resistance, its conductance will be 0.2 Siemens. So it's as simple as that. So as you can see, every single one of these numbers here is just the reciprocal of one of the many resistances we have in the circuit. So how do we fill out these boxes here? Well, let's take a look at the diagonal boxes first. So basically this first box here is saying, what are all the conductances that are hooked up to node 1? Well, what do we have? We have an 8th, a 20th, and a 6th. So we have an 8th, a 20th, and a 6th. And it's as easy as that. So following the same pattern, what's the conductance of that guy there? Well, oh, sorry, what are the numbers in that box there? And those would be the conductances that are hooked into node 2. So what are the resistances? Well, we have 4 ohms and 20 ohms. So the conductances is 1/4 and 1/20th. Oh, 1/4 and 1/20th. Ta-da! That's already 2 out of the 4 boxes done. How incredibly fun for us. Now, these other 2 boxes are slightly more complicated, but not very much. And you may have noticed, for those very observant of you, very clever, that those 2 numbers are exactly the same. And I need you to remember that because that's very important, and that'll come back in a second. So just keep that in your mind, brain, in your mind grapes, and we'll get back to that. So let's just do this box here first because why not? Basically, it's saying what's the conductance of the branch connecting V2 and V1, or V1 and V2, whatever. And the conductance is, of course, 1 over the resistance. And what's the resistance in between node 1 and node 2? It's 20. So the conductance is 1 over 20. Ta-da! And now you may be like, okay, well, it's 1 over 20. I got that. That's fine. Why is it negative? And if you need to know why it's negative, the reason is you got to think about where these numbers are coming from. They're not just being pulled out of the sky. Remember, these are actually coming from algebraic equations we wrote out. We wrote out KCL equations. So, if you don't remember, let's say, so in this case, the current would be this guy right here. What's the current there? The current is equal to V1 minus, just give me a second, sorry, minus V2. Oh, jeez. Minus V. My program is being very mean to me right now. Sorry about that. I think this will fix it. Woo, woo, wee. Yes, there it did. Ta-da! I'm a wizard. It's V1 minus V2 over 20. So why is it minus? Is because of this minus sign right here. And so this other box here, this guy right here, well, what should go there? Well, basically, it's the conductance of the branch in between V2 and V1, which is the exact same thing as the conductance of the branch in between V1 and V2, which is still 1/20th. And it's still negative for the exact same reason. And that's as simple as that. I mean, that's the whole thing. That's every box in this matrix equation here. So, great, you did it. Congratulations. You now know how to do nodal analysis by inspection. But I know what you're thinking. You're like, well, I mean, I know, but could you maybe show me an example? Could we go through this together so I can test my wizard skills? And the answer to that is absolutely, heck yes, we can. Here we go. So this is a slightly more complicated circuit. Um, and you may be looking at this and be like, oh no, I don't want to deal with this. Oh, so many things. But with nodal analysis by inspection, it doesn't even matter. This isn't even going to take that long. And when you get good at this, you could probably solve this in about 45 seconds. So let's go step by step. So the first thing you need to do with any circuit is identify the ground. Now I've already selected this bottom rail as my ground because I like it and I think it's pretty and it's the one that I want. But you can go ahead and choose any node that you want. Then, after we get the ground, we go ahead and choose our non-reference nodes. So we have to identify them, I suppose. And there's 3. Node 1, Node 2, and Node 3. So now that we have that, let's write out our big giant boxes here. Now this is a 3x3, so let's give ourselves plenty of room. That's a lot of room, but that's enough. That's fine. So there's going to be the matrix. There's going to be the vector of unknowns. And there's going to be the vector of known quantities. Now, once you get good at this, this is pretty much all you need to get started. But because you guys are new to this, I'm still going to label this and as the table. So just to help you guys visualize. So I guess first thing we should do is we should identify our knowns. In this case, this is a fairly nice, well-behaved circuit. So we only have 3. We have V1, V2, and V3. Great. So let's go ahead and just write out this as a table. V1, V2, V3, sources, and then V1, V2, yeah, and V3. So, which one do you think we should get started on first? I can't hear you, sorry, so I'm not going to take your suggestion, unless, of course, your suggestion was this one, because that's the one we're going to do. And why are we going to do that one first? Well, I like to do that one first because it's slightly easier, but more importantly than that, oh dear, I've just noticed something. I'm cutting off the bottom of this this matrix here on my capture, so let me just fix that. Let's see. So, like right there. Yeah, you can see that. Okay. Sorry about that, everybody. I am not paying attention. And so this vector should also be like right there. And I gotta hide my shame. I gotta hide it. Oh, I'm so embarrassed. Oh no, please. Okay, perfect. So, more importantly, the reason we're doing the source vector first is because if you're doing this on a calculator, you're going to be doing it first. You're going to want to put it in your stack first. Or at least you will if you're doing RPN, which is the greatest mode of all time. So do it. So let's go ahead and get started. So the first thing is, what goes into this box? Well, it's all the sources hooked into node 1. Well, what are the sources hooked into node 1? We got a 5 amps right there and a 3 amps right here. Okay, cool. So 5 and 3. So put 5 and 3 in there. 5 and 3. Now, you gotta notice what direction these currents are going. It's 5 entering and 3 exiting. So it's going to be positive 5, but it's going to be negative 3. So it's actually going to be 5 minus 3 in that section. Pretty simple. So what goes in this second box right here? Well, it's all the sources hooked into node 2. How many sources do you see hooked into node 2? 0. How great is that? We can put a big fat 0 in there, and 0 is a beautiful number. So finally, this box right here, what sources are hooked into node 3? Well, we got this 3 amps, and we got these 12 volts. So we know we're going to need a 3 and a 12 in there somewhere. So 3 and 12. Now, You got to remember that this is a voltage source, not a current source. So we need to convert it into a current source. How do we do that? We just put it over the resistance of the branch, which is 8 ohms. So it's actually going to be 12 over 8. And because the positive terminal of the voltage source is pointing towards the node, it's going to be plus 12 over 8. And of course, the 3 is also going to be positive because the 3 is entering the node. So that's it. We're already done the source vector. We did it. Congratulations. You're doing great. Awesome. Good job. So now we just have to do the matrix. And the matrix, again, is pretty easy. Let's do the diagonals first. You don't have to do it this way. That's not the way I do it, but I think it's a little bit easier to follow along when you're starting if you do the diagonals first. So let's do this box first. And it's the sum of all the conductances hooked into node 1, which of course is, so the resistances are 4, 8, and 2. So the conductances will be a quarter plus an eighth plus a half. Awesome. So what's in this box here? Well, it's going to be all the conductances hooked into node 2, which is going to be, again, a quarter, an eighth, and a half from 4, 2, and 8. Now, this circuit might trick you a little bit. The numbers across the diagonal there don't have to be equal. They just are equal in this case because the circuit is set up that way. It's just a coincidence. If, for example, this was not 2 ohms, it was 170,000, then instead of doing 1 over 2 here, you would do 1 over 170,000. Don't be tricked by this. These numbers don't have to be the same. And so for the third node, again, you got the 2 ohms, you got the 4 ohms, and you got the 8 ohms. So you do 1 over 2 plus 1 over 4 plus 1 over 8. Great. Let me just get my program to quit being dumb again. Perfect. So that's the diagonals. Now all we have to do is the corners, I guess. And we only have to do one because, again, this is a very nicely behaved circuit. There's no dependent sources. There's no weird transformers or transistors or anything weird in it. So it's a symmetric matrix. But just because we can and because it's a good check, we're going to do both sides. And that's the nicest thing about this. Although you don't have to do both sides, if you do and you get that the numbers are the same, then you've probably done it correctly. And if you've gotten that the numbers are not the same, you have a pretty good idea of where to look as to why they would not be and to see where you perhaps messed up. So what's this box here? It's the conductance between node 1 and node 2. The resistance is 8, so this is 1 over 8. And remember, it's negative. And if you want to know which boxes are negative, like when it's going to be negative, in circuits like this, anything that's not along the diagonal will be negative. And again, that's from the KCL equations we wrote out originally. So then this third box will be the conductance in between node 3 and node 1, which is 1/2. And it's negative. This box here is going to be the the conductance in between nodes 2 and 3, which is a quarter. Negative. And that's really all the information you need. You can just fill out the rest of the matrix from here. But again, let's just do it to make sure that we're not being idiots. So this box here should be the conductance in between node 2 and 1, which should be -1/8. This one here should be nodes 3 and 1, which should be -1/2. And this one here should be nodes 3 and 2, which should be -1/4. Are these numbers the same as these numbers? They are. So we've probably done this correctly. And then that's the whole thing. You solved it. You have the equations you need. Now all you have to do is somehow solve this this matrix equation. And you're probably going to get a calculator to do that for you. You can do it by hand. I wouldn't recommend doing it by hand. And if we do in fact do it with a calculator, you will see how beautiful this is and how easy and fast you will get the answers of V1 being equal to 10 volts, V2 is equal to 4.93 volts, and V3 is equal to 12.667 volts. There you have it. Congratulations. You are now a master of nodal analysis by inspection. Or you will be if you do a couple examples. You know, this one's a little bit less concrete, and it takes a little bit more time to sort of like get the knack of it. But once you do, you're golden, and you'll find nodal analysis way nicer than you used to. So have fun. Bye.